In this next video on factoring polynomials, we're going to look at factoring polynomials that are in quadratic form. Now with quadratic form, the idea is you can think back to Chapter 4 in our textbook, or Unit 1 that we've worked on, where we use the difference of squares or the British method or some combination of those things. So to factor this polynomial, x to the fourth minus 81, the first thought is, as I've seen the sum of cubes and the difference of cubes, is this a difference of cubes pattern? Well, no, because 81 is not a cube and neither is x to the fourth. But what I do notice is that 81 is a perfect square, and x to the fourth might be a perfect square as well. When I say that, I know it looks kind of goofy, but think about this. If I took x squared and squared it, I would have x to the fourth, correct? And if I took 9 squared, that would equal 81. And I notice that I'm taking the difference of these two things, so I would bet that this is going to be a difference of squares pattern itself. Here's what I mean. When using the difference of squares pattern, we have two binomials with the roots of the first square. All right, x to the fourth is x squared squared. So I'll put an x squared first here and an x squared first there. And then the square root of 81 is 9, because 9 squared is 81. So I'll have an x squared minus a 9 and an x squared plus 9. And that was using the difference of squares factoring pattern. Now sometimes, as we mentioned earlier in a couple of these videos, is we need to always beware of the difference of squares. So as we look at these two expressions, does the difference of squares happen again? Well, this is x squared plus 9, so not here, but this x squared minus 9 is another difference of squares pattern at work. I need to factor this further. X squared is the square of x, 9 is the square of 3. So x minus 3 and x plus 3 would be the smaller factors of that expression. And then the x squared plus 9, because it's not a difference of squares and there's no sum of squares pattern, is x squared plus 9, and needs to be included in our answer as well. This expression is fully factored. So even though it wasn't quadratic in nature, it behaved like a quadratic function because I have something squared to start it off. Now this next example, I noticed there's 3 terms, and when I had to factor 3 terms, sometimes the way I did that was using the British method in the previous unit. So as with all factoring, you should always look for a greatest common factor that can come out first. Because if it doesn't look like something that can be factored, it may be that there's a greatest common factor that needs to come out, and it will then make things a little more obvious. So between 15, 72, and 108, I think 3 goes into all of those. And x to the fifth, x cubed, and x to the first, I believe that x to the first goes into all those. So I'm going to start by factoring out 3x because that's my greatest common factor. That will leave me with 5x to the fourth minus 24x squared and minus 36 at the end here. So now that I took out the greatest common factor, now this looks like something that might be in quadratic form because I have x to the fourth and then x squared and then 36. That'd be as if I had, you can't see that, if I had 5x squared minus 24x minus 36. So even though it's x squared and x to the fourth, this term right here, x squared, is the square of this variable here. So x to the fourth is the square of x squared, and I have a constant at the end. This is going to behave like a quadratic function would and can be factored just like this quadratic function would. So I'll erase that. And we'll get to factoring using the British method. So I'll start by multiplying the first term times the last term, which will be negative 180 x to the fourth. Now the variables here are key. I then need factors of negative 180 x to the fourth that add up to negative 24x squared. Well, I believe that will be negative 30x squared and positive 6x squared. And again, it might take a little bit of work to find those factors on your calculator, but that's okay. Key again being, because it was x to the fourth, I need x squared here and x squared here. Adding those would give me the negative 24x squared that I have right there in the middle. Now, I bring down the outside terms, 5x to the fourth, and a minus 36 at the end. I've turned my 3 terms into 4 terms, so now I'll use grouping to factor those a little bit further. First pair, GCF, is 5x squared, leaves me with x squared and minus 6. Second pair, GCF, will be just 6, so I'll take out positive 6, which leaves me with x squared minus 6, which again, I'm supposed to have that same thing inside of the parentheses, which is good. So now as I write out my final expression, x squared minus 6 is one of the factors. The other factor will be 5x squared plus 6. And we shouldn't forget about the 3x that we took out way at the beginning. So I should put 3x in front here. Check. Do I have a difference of squares here? I see a minus sign, I see a square, but 6 is not a perfect square, so I'm good to go here. And these, I'm adding a square, neither are perfect. So this looks like I'm all done. Now at the bottom here, you see a couple of factoring tips. And oftentimes the number of terms gives away what you're supposed to do. If there are 2 terms in your polynomial, you will probably use the difference of squares or maybe the sum or difference of cubes. If there's 3 terms, I would bet that you'll be using the British method like we did just here. And if there's 4 terms, you should be awfully happy and rejoice a little bit because you get to use grouping. And grouping is probably the easiest thing that we get to do when it comes to factoring. So that's factoring in quadratic form.